All right. So last semester we had left off talking, or the last thing we talked about were polynomials, right? And we spent time talking about how to add, subtract, multiply, divide, factor, and solve polynomials, right? That was kind of the last set of topics we had spent time doing. This semester we're starting off and we're going to pick up and talk some more about factoring and solving polynomials. This is the place where we're going to spend some more time. So if you remember from last semester, when we talked about factoring and solving polynomials, specifically we spent time working with that factoring tree, right? I'm going to redraw that now and talk about it a little bit now. If you already have it in your notes, you don't need to write it down again. If you're like, oh, I don't have that anymore, feel free to write it again. Or you're like, no, I just copy everything. It doesn't matter. That's fine. So what this was kind of like a guide to help you factor some of these polynomials. So we start with some polynomial. And then we look at the number of terms in the polynomial. And we had three possible outcomes. We had that there were two terms, that there were three terms, and that there were four terms. Right? So if we were going down the two-term branch, the first thing we wanted to check is if it's a difference of two squares. If it was yes, we factored it, and then we went back down this two-term branch again to see if there was any more factoring that we could do. If it wasn't a difference of two squares, then we had to check to see if it was a difference of two cubes or a sum of two cubes. If it is, we factored it using that pattern, and then we went back down that two-term branch again. And if it wasn't, then we were finished. For the three terms, the first thing we had to check is it in the quadratic form? If we said no, then there wasn't any more factoring we could do. We just finished. If it was yes, then what we had to do was try to factor it like a quadratic. So if I was factoring something like a quadratic, there was two situations that I cared about. When the leading coefficient was 1 and when the leading coefficient was not 1. So if the leading coefficient is 1, we just need to find the two things that multiply to give us the constant term and add to give the middle term. We called that the short factor. If it is factorable that way, we factor it that way, and then we have to check to see if any of those two-term pieces can factor more. So we have to go check down the two-term branch. If it wasn't factorable using the short factoring, then we were finished. If the leading coefficient is not 1, we had to do that long factoring. So here we looked at the two numbers that multiplied to give us the leading coefficient times the constant term, and then added to give us the middle term. And then we used those two numbers to do factor by grouping. And a similar thing happens here. So if it's yes, then we go to the two terms branch. And if it was no, then we were finished. And then the last branch was the four terms. And then we had only one option here, which was factor by grouping. If we could do that, then we just go to the two-term branch and check to see if there's any more factoring. If it wasn't factorable by grouping, then we were just finished. So this was kind of our descriptor or visual for how we were planning on factoring these polynomials in the first semester. Now, there's a couple of situations that are not very satisfying. So, for example, we just stopped if we had a three-term polynomial that was in the quadratic form or wasn't in the quadratic form. We didn't have any way to deal with that. That's something that we need to kind of fill in. For a four-term polynomial that we can't factor by grouping, we didn't have anything else to do, so we just stopped. We're going to fill that in. And then if we had five or more terms, we didn't have anything to do with that, and we're going to have to fill that in. So this next week or so, we're going to work on extending this factoring tree to cover some of these situations that we didn't address in last semester. Specifically, how do I factor something that's got three terms but isn't in the quadratic form? Or how do I factor something that has four terms that I can't group? Or how do I deal with something with five or more terms? These are all important situations that we need to kind of address. So that's going to be kind of the goal here for the next week or so, is to figure out a way to kind of extend these little parts of our factoring tree and develop a new method to kind of cope with those situations. Is everybody okay with the idea there of kind of what we're going towards or what we're building towards? Okay. So before we pick up and dive into that, I want to do a little bit of vocab. And I'm not going to define any of these vocabulary words specifically because they're all kind of terms we've already used. But what I'm really more interested in doing is like showing you the relationship between some of these terms. Okay? So let's just say, for example, I have the polynomial x squared plus 7x plus 12. Right? So that's an example of a polynomial. Specifically, it's a quadratic polynomial, but it's still just a polynomial. Is this polynomial factorable? This should be something that's easy to factor, and we can do this in our head. What does it factor to? So the two numbers that multiply to give me 12 and add to give me 7 are 4 and 3. So the factored form I'd write is x plus 4 and x plus 3. So each one of those we would call a factor. Everybody agree with that? Okay. What if instead we had x squared plus 7x plus 12 equals 0? This is now a polynomial equation because there's an equal sign involved. So if I solved this polynomial equation, what would the answers be? Should be able to do this now quite easily. Very good. -4 and -3. How'd you do that so fast? You used the factored form and set each of the factors equal to 0 and solved. Good. So these guys are solutions then. And notice the relationship between the solutions and the factors. If I know the factors, I can get the solutions really easily. Or if I know the solutions, I can build back out the factor, right? We can see that. Okay. If I have y equals 7x plus 12, what can I do with something like this? I can graph something like that, right? So if I graph this, this is going to be like the graph of a polynomial. And in particular in this graph, these points are going to be of interest to me. What are these points called? They have a special name. Look at where they're crossing. They're crossing which axis? The x-axis, so we'd call them x-intercepts. And guess what the location of those two x-intercepts are? It's at -4, 0 and -3, 0. Do you see a relationship between the x-intercepts and then our solutions to the polynomial equation and the factors for the polynomial? Yeah, definitely do, right?
Yeah.
And what if we have, say, f of x equals x squared plus 7x plus 12? This is a polynomial function because of the f of x there. And I know for a function I can evaluate them. What would I get if I did f of -3? What would I get? What does f of -3 mean? Let's start there, maybe. Good, I'm going to plug the -3 in the spot where the x's are. When I do that, what number am I going to get? Should be easy, based on the things we've already done. Why is it going to be 0? Well, if -3 is a solution, if I plug -3 back into the equation, I should get 0 back from it, right? So that's what we're doing here. So we call these guys -3 and -4. These are zeros for the polynomial. Yes, Eli. Of course. So the point of this is that I can use one of these pieces of information to find the other three, right? If I know a 0 for the function, I would also know a factor for the polynomial. I know a solution for the equation equal to 0, and I would know an x-intercept. Everybody agree with that? And it doesn't matter which one of those 4 you're looking at. If I have one piece of information, I can use that to get information in the other 4 situations. Does that make sense? So, of these 4 situations, the graph, the polynomial, the equation, and the function, which one of these is going to provide the most information? The factors, the solutions, the graph, or the zeros? The solutions end up giving us the most information. What kind of answers can I get for the solutions? I can get things like -4 and -3, right? But what else can I get? And also imaginary. That was the only option left. Yes. So these can be imaginary, right? Are we ever going to have a factor with an imaginary number in it? We've never seen that happen, right? Can we have an x-intercept with an imaginary number in it? There's not even a place on the xy axis to put imaginary numbers. Definitely not. Have we ever plugged an imaginary number into a function before? No, we haven't done that. So like the only place we've seen those imaginary things pop up is when we've done the solving part. So we have to be a little bit careful there, because if we're talking about solving and we're using the graph to kind of get ideas of what solutions might be, we might be ignoring possible imaginary solutions. Okay? So that's worth keeping in mind. But this is going to be one of the tricks that we're going to use to kind of factor some of these situations that on the factoring tree that we didn't have a way to address, is instead of thinking about this as a factoring problem, maybe we think about it as one of these other type of problems and can get some insight as to what potential factors might be there. Everybody okay with that idea? Okay. So our first main tool that we're going to use is called the factor remainder theorem. And it says that if f of x divided by q of x has a remainder of 0, then q of x is a factor of f of x. So let's look at an example of kind of how we can use this. And I'm going to build out an example of something that I know is going to be factorable, but I can't use the factoring tree on to kind of help illustrate this. So I'm just going to pick the polynomial that's made up by the factors x plus 2 times x plus 3 times, or I'm sorry, x plus 1 times x plus 2 times x plus 3. So I'm going to put this into standard form. So I'm just going to multiply this out. This looks like a problem that we would have done last semester. So to multiply this out, I'm just going to use the associative property and multiply these two factors first. So how do I factor, or how do I multiply something like x plus 1 times x plus 2? What's the name of the process I use there? It's got 4 letters. FOIL, yeah. So when I do that, I get x squared plus 2x plus 1x plus 2. And then I still have the x plus 3 at the end. And if I combine my like terms, I get x squared plus 3x plus 2 times x plus 3 still. This also looks like a problem that I would have done last semester. What did we say was going to be the, at least what did we do for, or how do we multiply something like this last semester? We made a grid, right, to kind of keep track of everything. Okay. So let's see, if we multiply then inside our grid, oops, what's there? And then if I combine my like terms, I get that x plus 1 times x plus 2 times x plus 3 is x cubed plus 6x squared plus 11x plus 6. So if I look at this polynomial here, x cubed plus 6x squared plus 11x plus 6, this is a 4-term polynomial, right? If I try to factor this by grouping, it's not going to work. Let's just demonstrate why real quick. So I maybe start by making my 2 groups. From the first group, maybe I try taking out an x squared. From the second group, the greatest common factor between 11x and 6 is just 1. And now there's no more place for me to go because these parts are not the same, right? So I'm stuck. I couldn't factor this by grouping. However, I know this polynomial is factorable because I know that it's equal to x plus 1 times x plus 2 times x plus 3, right? There's got to be some way for us to be able to do that factoring. That's kind of what we're going to be building towards over the course of this week. Now, I gave you guys just a moment ago this factor remainder theorem that I've said is going to be somehow quite useful for us to deal with these sorts of situations. So what the factor remainder theorem said is that if I take some function and divide it by another function, if I get a remainder 0, the divisor was a factor of the dividend. And if it's not a remainder 0, then the divisor wasn't a factor. So let's just look at how we can use this. And to do these examples, I'm going to use this polynomial that I just created for you guys. So maybe we ask, is x plus 4 a factor of this polynomial x cubed plus 6x squared plus 11x plus 6? So we know from the factor remainder theorem, I'll just abbreviate that as FRT, that we'd answer yes if x cubed plus 6x squared plus 11x plus 6 divided by x plus 4 has remainder 0. And then we'd answer no if it's not 0, right? Okay, well that's easy enough to do. We talked about polynomial division last semester. So let's worry about dividing these two polynomials. So last semester we talked about two types of polynomial division. We talked about long division and we talked about synthetic division. Which one of the two would be the best choice for this problem? Synthetic division is faster, but I can't always use the synthetic division, right? What do I have to have in order to do the synthetic division? The divisor has to have degree 1, which it has, and leading coefficient of 1, which it also has. So synthetic division seems the appropriate choice here. So I'll start by drawing my synthetic division bar. What number is going to go on the outside of the synthetic division bar? -4. How did you get that, Zach?
Because x plus 4
Excellent. So we just set the divisor, in this case x plus 4 equal to 0, and solve. The solution there is going to go on the outside. What numbers are going to go on the inside? One, 6, 11, and 6. Where did those numbers come from? They're the coefficients from the dividend, right? Okay. So we start the synthetic division process by bringing down the first number, and then we take the -4, we multiply it to the 1, and we write it in the next spot, and then add down. And then we just keep repeating that process until we filled in all of our spaces. So -4 times 2 is -8. -4 times 3 is -12. And then we remember here, this number is the remainder. And since that's not equal to 0, I know x plus 4 is not a factor of x cubed plus 6x squared plus 11x plus 6. Everybody okay there? Now, we already kind of knew that because of the way we created this polynomial, right? We know this polynomial's factors are x plus 1, x plus 2, and x plus 3. Because that's the 3 that we multiplied together to create it, right? Because we wanted to start with something that we knew was going to be factorable to kind of explore what's going on here. Well, let's check if x plus 3 is a factor of x cubed plus 6x squared plus 11x plus 6. So for the same reason, I'm just going to start by dividing the polynomial by the factor, or the potential factor. And again, since this is, the divisor has leading coefficient of 1 and degree 1, I can just use synthetic division to do this. So what that tells me then is x plus 3 is a factor of that polynomial. We knew that because of the way we created that polynomial, that x plus 3 was one of the 3 things we multiplied together to make it. But this actually tells me more than just that x plus 3 is a factor. So, as an aside here, if I did 18 divided by 3, I would do like a 3 here and 18 there, and I'd put a 6 and do something like this and say that 18 divided by 3 is equal to 6, right? Is that equivalent to saying 18 is equal to 6 times 3? Right? That's the same thing, right? So let's use that same idea, the relationship between multiplication and division, for this problem. Since I know that x cubed plus 6x squared plus 11x plus 6 divided by x plus 4 is equal to constant term, x coefficient, x squared coefficient, I can say then x cubed plus 6x squared plus 11x plus 6 is equal to x plus 4 times x squared plus 3x plus 2. Right? Just like we did with 18 divided by 3 equals 6 is the same thing as saying 18 is equal to 3 times 6. Look at what we've done here. We've partially factored x cubed plus 6x squared plus 11x plus 6, right? We were able to peel off one factor, and we're left with another polynomial. But look at that other polynomial that we have here. Can we factor that one? X squared plus 3x plus 2? Yeah, that's just a quadratic, right? We spent like a whole chapter factoring these things. How does that one factor? X squared plus 3x plus 2x, or 2, excuse me. Two numbers that multiply to give me 2. Add to give me 3 are 2 and 1. So my factors would be x plus 2 and x plus 1. And I made a little bit of a typo here. I need to go back and fix this real quick. So for some stupid reason, I divided x plus 3, but I wrote x plus 4 here. I don't know why I did that. Great googly moogly. So what we've just done is we've created a factoring technique that we can use. So let's see an example of using this dividing process that we've just kind of established to actually do a factoring problem that we don't know what the factors are going to be in advance. So here we're asked to factor x cubed plus 2x squared minus 13x plus 11, given that x minus 1 is a factor. So I'm going to use this as my key. Since I know that x minus 1 is a factor, I know that I can use the factor remainder theorem and divide my polynomial by that factor. And since x minus 1 has a leading coefficient of 1 and a degree of 1, I can do synthetic division to do that do that dividing. Oh, I copied down my problem wrong here. Sorry again, guys. That was supposed to be 10, not 11. Jeepers creepers. So I got a zero remainder, which I knew I was going to get. How did I know that I was going to get a zero remainder for this division problem? Yeah. Since x minus 1 is given as a factor, I know by the factor remainder theorem I'm going to get a zero divisor. So I knew that was going to happen. What I didn't know was what this part was going to be. So after doing this division, I can say that x cubed plus 2x squared minus 13x plus 10 factors to x minus 1 times constant x coefficient, x squared coefficient to that. Everybody okay there? So the division allows me to partially factor, and then I just need to look at this piece and see if I can do any more factoring. Am I guaranteed to be able to factor that more? No, right? Not every polynomial is factorable. Is this one factorable, though? Well, since it's a quadratic and its leading coefficient is 1, I would just need to find two numbers that multiply to give me negative 10 and add to give me positive 3. Are there two numbers that do that? 5 and negative 2. So my two factors would be x plus 5 and x minus 2. So that's my final answer. Everybody okay there? Okay. What if I had then asked you to say solve this problem? Well, we already know that it factors by the previous example. And if I have it factored and equal to 0, is this a difficult problem? Heck no, it's not. I just applied the zero product property and set each of these factors equal to 0. And we're done. So if we can factor something, it's very easy to solve it, right? Okay. That's going to be that for today.